So first of all, thank you so much to the organizers for the opportunity of being here presenting this talk, which is about norm-attaining in projective tensor products. And this is a joint work with Luis Carlos García Lirola and Abraham Rueda-Zoca, which has been recently published. So let me start by reminding some concepts. Consider three vector spaces and a bilinear map between the Cartesian product of two of them into the third one. We denote in this way the space of bilinear maps. But as you know, bilinear maps are not as good as linear ones. So we would like to linearize bilinear maps. And for this purpose, we need tensor products. So for every pair xy, we consider the linear functional, which is just the valuation over bilinear functionals, and define the tensor product as the space spanned by those elements, which is in the algebraic dual of bilinear functions. So in general, a tensor would be a linear combination of those elementary tensors, and this representation is not unique, and this will cause some problems in the future. And we can also define the action of a tensor on bilinear maps in this natural way. And which is beautiful is that the value is independent of the representation of U. And as I have promised, with this construction, we can linearize bilinear maps in this way, obtaining the commutative diagram. For each bilinear map, we can define a linear map, but now define it on the tensor product in this way. And conversely, we can recover our original bilinear map just by composing with the tensor map between the Cartesian product and the tensor. Okay, this diagram I think is nice, but since the title of the conference is structures in Banach space, I think everyone will be happier if we endow the space with a norm. So let's assume x and y are Banach and define a norm in this space. It's reasonable that the norm should verify this condition, and thanks to the triangle inequality, we should have this inequality for every representation of U, which has a lot. So the biggest candidate for a norm is the projective norm, which is defined as the infimum of the sum of the norms of x and y, and the infimum is taken over all the representations of the tensors. Unfortunately, this space is not complete unless x or y are finite dimensional. So in general, we have to consider the completion of the space, and is what we call the projective tensor. And the good property of projective tensor product is that we can obtain the same diagram as before, but now with bounded bilinear maps. A bilinear map is bounded just if its norm is finite. And with the same arguments as before, we obtain the same diagram, but now the norm is preserved. So we have these isometric identifications between the space of bounded bilinear maps and the space of bounded linear operators in the projective tensor product. And when Z is just the scalar field, we also obtain an identification with bounded linear operators from X to the dual of Y. And we also have a characterization of the unit ball of the tensor product as the closed convex hull of the products of the balls. So what is norm attainment in this context? Given a tensor in the completion, we can obtain an expression for this projective norm. You can see that this is the same expression, but now we are considering infinite series, where before there are finite sums. And we ask where this infimum is in fact a minimum. So we will say that a tensor attains its projective norm if there is a representation where the norm is attained. And consider the set of norm-attaining tensor, and study the size of this set in the sense of looking for spaces x and y such that this set is the whole space or at least is dense. Since this topic has been studied for different researchers, let me present some of known results. Dantas, Young, Roldan, and Redazoka, which introduced this norm-attaining notion, prove that every element is norm-attaining when x and y are finite dimensional, when one of the factors is literal one and the other is just any Banach space, or when x and y are the same complex Hilbert space. In fact, in the finite dimensional case, Pelczynski and Tomczak-Jägerman prove the minimum number for the optimal representations, which is the product of the dimensions or this quantity, the double of this quantity when the scalar field are the complex numbers. In general, we are going to work with infinite dimensional spaces, so this won't, we are not being so worried about it, but it's interesting. And Dantas, García Lirola, Jung, and Redazoka prove that we have also every tensor norm-attaining when X is a finite dimensional polyhedral space and Y is a dual. I would like you to remember this second case of little L1, and this is because we have the identification the tensor product with the absolutely summable sequences in the space Y. Okay, and as you can imagine, there are some examples of spaces XY where we have tensors don't attaining its norm, and we can characterize this norm attainment in the following sense. A representation would be optimal if there is an operator with norm 1 that attain its norm in every elementary tensor. And thanks to this characterization, they prove that if every element attains its projective norm, then every operator in this way can be approximated by norm attaining. So there are examples of spaces where there are tensors that do not attain its norm. For example, LP with the Gauss space, or the two-dimensional Euclidean space with capital L1. And another interesting example was proved by Abraham that when we consider the tensor C0 and little l2, we obtain that the norm-attaining tensors are in the algebraic dual. It means they are finite sums of elementary tensors. And we don't know if this content is strict or is the whole algebraic dual. Well, now we can present some new results. First of all, it's important to remark that projective tensor product does not respect subspaces in the sense that the norm is not preserved. However, when we have one complementability, everything works well, and we could prove this result, which in particular implies that we can get rid of the assumption of duality in those theorems and change by assumption of one complementability in its B-dual, which is a weaker assumption. And one of our main results is the following. We consider a predual of little l1, and for every subspace of set, and Y being any Banach space, under approximation property assumptions, we have that every element attains its norm when we take the dual in both factors. This theorem generalizes in some way the case of little l1 because now we are considering subspaces, and it also generalizes the result when one of the factors is a finite dimensional polyhedral space. I cannot present the whole proof, but some key elements. In the tensor product, we can also define the injective norm that has the nice property of respecting subspaces. Then the isometric invariant times the identity is a linear isometry. We also have this identification between the dual of the injective tensor product and the projective tensor product of the duals. And finally, we use this lemma, which states that the adjoint of a linear isometry is a quotient operator, but we could also find for every x star a preimage that preserves the norm. And with all of this, we can take a tensor in the space. By the lemma, there will be a set in this space where one of the factors is literal 1 with the same norm as U. But in this space, every tensor attains its norm, so set attain its norm, and we can conclude that U also does. And this is just the same result, rewritten with the one complementability assumption. This theorem allows us to give some consequences. First of all, one of the classical reduals of literal 1 are C of k, where k is scattered and compact. So we could obtain this corollary. And which is important to remark is the hypothesis of being scattered cannot be removed. Because when we consider the unit circle of the two-dimensional Euclidean space, we find tensors that do not attain its norm, and the other factor is just R2 with the Euclidean norm, so it's not an easy and a hard space. And the other consequence, which is not trivial, but the other consequence came in terms of Lipschitz free spaces that has been introduced by Abraham and Eva, so I hope everyone remember. And when we consider one of the factors being a Lipschitz free space and the other one just one complemented space individual, we have that every element attains its norm in two cases. One of them if M is countable and proper, and the other one if M verifies all those hypotheses that are a bit hard to imagine, so I'm going to present an image of such a space. Let's consider a graph, okay, where we have a point 0, a point set, and a sequence. We put every distance to be 1, except from 0 to set that we have distance 2. This set is uniformly discrete, is countable, and the set of distances is a compact. And if we consider the topology such that the sequence converges to the first element and the rest of the points are just discrete, we have the other hypotheses that are D is lower semi-continuous in this topology, and the space is compact. So this metric space satisfies the hypothesis of B, and the Lipschitz free is not isometrically isomorphic to literal 1, so this case was not considered in the previous theorems. For the last part, we say, okay, the condition of every tensor attaining its norm, it's not easy to satisfy, so why don't we reduce our pretensions and study where this set is dense? And this is motivated by the following example. If we consider capital L1, which has the same isometric identification as this one with the projective tensor products, and consider simple functions where we have representation with disjoint, with pairwise disjoint sets, we obtain that this representation is optimal in the sense that F attains its norm as a tensor. Okay? And since simple functions are dense, we have density of norm-attaining tensors. But, however, there are also spaces X and Y where we don't have density. These spaces are not easy, are a bit weird, so these are good news. And the next question would be, reflexivity in both factors imply density in the norm-attaining tensors? And the answer came a year later with a positive answer, because they prove that if x and y are duals with the Radon-Nikodym property, and at least one of them has the approximation property, then we have density. In the search of other spaces verifying this density, they consider the metric property, which states that for any finite finite number of points in X, we can find a finite dimensional one-complemented subspace that approximates those points. Or equivalently, there are finite rank projections with norm 1 that converge to every point. As you can see, metric property is going to behave well with projective tensor products because we have finite dimensional and one complementary. And indeed, it does, because they could prove that we have density in norm-attaining tensors where X has the metric property and Y has the same property or is uniformly convex, or when X is also polyhedral and Y is a dual. And what we do is to generalize these results in just one theorem, where the hypotheses are very similar to the metric property, but now we are also assuming that when we take finite dimensional subspaces, we have density of those norm-attaining tensors. And this theorem also provides new examples that were not known, as for example, if one factor is upper dual of capital L1 and the other is one complemented individual, then we have the density. Or if X has the metric property and Y is a dual with the Radon-Nikodym property. And to finish, just to state some open problems. First of all, we wonder if every extreme point of the unit ball is an elementary tensor, which will be the analogous of what Eva has told about Lipschitz free spaces. It's an open question. For example, how are Banach spaces X such that every tensor attains its norm for every Banach space? We give a necessary condition for this to happen, but there are a lot of work to do in this question. And finally, if there are reflexive Banach spaces where there are tensors that do not attain its norm, because all examples known where this happens, one of the factors at least is not reflexive. So we don't know if reflexibility implies this equality. And that's all. These are some of the main references. Thank you so much for your attention. Yeah. Mm-hmm. I'm not sure, but I think it's interesting. What we do in these cases is to use the previous corollary and embed the Lipschitz free in a CDK. Sorry, the per-dual of the Lipschitz free in a CDK, and then we have the result. But maybe there is another generalization. Into.
No widzisz, właśnie. Wszystko jest opisane. Wszystko jest wszystkie są na stronie tej, na Google Sites.
Że wypadałoby dodać jakąś zmiankę ESI, żeby się gdzieś pojawiło.
Ja nie wiem. Tego nigdy nie robię, żeby pisać nazwę konferencji, bo potem jest problem z...
Aha, mówisz, żeby te potrzebują.
Ja myślę, że lepiej dla nich, jak jest w artykule gdzieś wpisane. Jasne.
Nie wiem, jak to się tu wiąże.
Tak. Po prostu na uszy i tyle.
I tyle. Aha. Tak?
Do góry,
Na głowy?
Ja ostatnio coś takiego miałem.
Na dół. Tylko żebyś na uszy zahaczył te haczyki.
Dobra. Aha, tak, dobra. Ja zaplątałem sznurka kiedyś tam. Zakończyło dziwnie. Nie, też nie lubię. Mnie się wydaje, że to i tak nic nie słychać więcej. Widziałem na końcu, to nic nie słyszałem. Tak, tak. Ale on mówi głośno w ogóle. Albo może miał podkręcone to. Dobra. O, dobrze, działa. Działa, dobra. Taką złączkę sobie kupiłem i w Pradze chciałem podłączyć się do internetu tego kablowego i nie przechodziło. Mam. Nie, mam tylko na to. Mam ten taki malutki ten laptop teraz, wiesz, ten z USB tylko. No i niestety, no ale jakoś sobie dałem radę. No tego nie włożę do laptopa już. Bez łączki. Ale już to takie mam. No tylko to mam. Tylko to. No właśnie, to jest zadziwające. No nie, chciałem mieć nowoczesny, to mi tak unowocześnili, że słyszałeś, że konferencje, te arkady, ktoś tu wspominał, że w lecie organizuje się konferencję dedykowaną Gulką w Tomsku. Ale online, no bo to nikt nie może tam dojechać. No i teraz jest problem, czy się włączymy do tej konferencji. No ja wiem. No ja, no wiem. To, no właśnie. No, Marian poszedł jeszcze dalej. On już nawet uważa, że nawet nie powinno się oznaczać w pracach literką dużą Z jakichś obiektów. To już jest, wydaje mi się, przesadą. A? Ja nie wiem, czy to jest dokładnie czas, bo...
Nie, ja się śpieszy.
Aha.
Ale jakoś tak się te paki zaczynają w lokalnym czasie.
No nie, no dobra, w tym tutaj, bo trudno korygować później to, co tu się dzieje. Dobra, zaczynamy.
Okay, so the next here's a contour.
So thank you very much. So my talk is based on the joint work with Christa Vargas and Damian Sobota. In fact, it's one chapter of a long paper about operators, continuous operators on the Banach Spaces or Lipschitz functions. So it's only one chapter, and even some selected part of the chapter, not everything. So let's start to recall this principal definition. A Banach space is called to be a Grothendieck space if every weak star is converging sequence, the weak star topology, and the dual converges in the weak topology. This is the definition. It's already now to Grothendieck that any Banach space with that property, which is not reflexive, should contain little L1. So Diestel conjectured that each non-reflexive Grothendieck space contains L infinity, or at least have a quotient to L infinity. And then Haydn constructed in ZFC a Grothendieck Banach space Cx without a copy of L infinity. It was a result of Haydn, and it was not mentioned inside if this compact contains beta n or not. But Poschmider and Schellach proved that this Haydn space contains beta n. So that means that Banach space has a quotient isomorphic to infinity. On the other hand, Palagrand under CH constructed the compact space without beta n, such that the CX is Grothendieck, but without copies, without quotients isomorphic to L infinity. In fact, this result has been proved. It's not the final step, because Damian and Lubomir, they proved that such object using some forcing without CH. So more or less, the work is still improving, what I know from even some parties, including our monograph. Okay, so anyway, if we add Martin axiom and negation of CH, and it was already mentioned probably yesterday, every non-reflexive Grothendieck space has a quotient isomorphic to L infinity. This is a result due to Haydn, Levy, Odell. Okay, so now it's well known that for any infinite compact X, this Banach space Cx contains little C0. And if we apply some result like we have here, a Banach space with the property V of Pełczyński is Grothendieck if and only if it does not contain complemented copy C0. Just to recall, what does it mean, the property V? This happens if any unconditionally converting operator to any Banach space is weakly compact. So fortunately, every Banach space Cx has property V, so therefore, for free, we have this nice characterization of Sembranos stating that Cx is Grothendieck if and only if Cx does not contain a complemented copy. But if we work with product of compact spaces, you see completely different story. So this space is never Grothendieck because of this result of Sembranos and Fringe. So the same problem will be studied in my talk, what I said is part of our long paper with Damian and Christian, for Lipschitz Banach spaces, Lip0, so-called Lip0 over metric space M. Okay, I think these definitions were already announced. Yes, so just only to recall that we concentrated on this object Lip0M with real valued Lipschitz function with fixed point E. And the norm is just Lip-F. Of course, this cannot be, the first situation is totally different from the second one. But anyway, the class of Lip0M seems to be more interesting because of several applications. This free Banach space was already defined maybe twice. Anyway, this is the FM is predival of Lip0M. By the way, Lip0M having this information about 4, the Lip0M with pointwise topology sigma compact and densely embedded in space CP over, I mean with pointwise topology, continuous function over this space M. Okay, so let's start with very principal, very interesting, very essential result also of my talk. So this is a result due to Hayek and Novotny. If we deal with an infinite metric space, then this Lip0M contains isomorphic copy of L infinity over density of M. Consequently, the predual contains a complemented copy of L1 dm, and this makes essentially improvement and essentially key point to get some next observation, to get some new some results. So, and this is something which is really striking and very strange. Apart the case, what is mentioned here, lib 0 over 0, 1, there is no known example of Lipschitz lib 0m, which is a Grothendieck space. I asked several people, including Michał Docha, and we asked with Christian several people. I think still is the same situation. I would say even I could stop here my talk because we have only negative results, nothing else. We hunted for some cases of Banach spaces to show how to prove that lib 0 over something is not Grothendieck, and so on and so on. But with Fm, situation is totally different. So this space is never Grothendieck, doesn't matter what is M. Why? Because we know from Novotny-Hayek theorem that Fm contains complemented L1 over dm, so consequently contains complemented copy L1. So the next is just to realize that, or to recall very well-known fact already to Grothendieck, that complemented subspaces of Banach spaces with the Grothendieck property are Grothendieck. And L1 fails the Grothendieck property also owing to very classical statement telling that every separable Banach space, which is Grothendieck, must be reflexive. So we have for free, using this Novotny-Hayek theorem, that Fm are not Grothendieck. So also for lib 0m, Zambrano's theorem doesn't help because Fm prime and the dual is isomorphic to lib 0m, and this also I think this is a result of Besaga, that the dual Banach space never contains little zero complemented. So always we have the lib 0m doesn't contain complemented C0. But still we don't have any information about Grothendieck property for lib 0m itself. Okay, so next is nice also a result of Rebiger telling that a Banach space is Grothendieck if only if the dual is weakly sequentially complete and E has no quotient isomorphic to little C0. So if we have it, there is some strategy. If you are going to show that this concrete L0m is not Grothendieck, we can use two situations, either to look for a quotient of lib 0m isomorphic to little c0, or to show that the dual is not weakly sequentially complete. So it's another. Now, if we try to look at lib 0 over Banach space, situation is a little bit easier because lib 0 always contains complemented dual. So if we know that we have a Banach space and the dual is not Grothendieck, then the space lib 0 over E is also not Grothendieck. There's another rescue operation just to get something negative. Okay, so in principle, if we know that there is a continuous linear map from lib 0m onto little l1, then we know already that our object is not Grothendieck. So the one line of research is just to think about possible situations where we can map this lib 0 E onto L1. So we collect some quite simple situations to show that the most interesting, the most common objects are out of the business. So, for example, if we have a Banach space for which there is continuous linear surjection from the dual onto L1, then this is the case. The other situation, our space is separable, E is separable, contains isomorphic copy of pre-dual L1. Also, this is because we are using so-called lifting property, will be announced on the next page. The third is totally trivial. Yeah? The fourth is involving here the property V. So that means, in fact, if our space has property V and is not Grothendieck, so that means our space E contains complemented little c0. So that means the dual can be mapped onto L1, and the first item appears here. Yeah? So it's just collection of quite natural situations. Corollary says the following: if we just look at this very concrete two cases, little c0 or little L1, that our spaces is not Grothendieck. It's not Grothendieck. Okay, so next. So if we know already, this is also coming from Rebiger theorem, if the dual is not sequentially complete, is not weakly sequentially complete, then our space is not Grothendieck. So now, if we consider a separable Banach space, which is not weakly sequentially complete, then the lip 0 over this space is not Grothendieck. Why? So we have here a special situation. Our Banach space is separable. Therefore, we can use the lifting property. Is nice information coming from it should be Godefroy, some misprint. Godefroy-Carlton theorem stating that for a separable Banach space, we have so-called lifting property. So our space is not only isometrically embedded in the predual free Banach space, but even this isometry is linear. So having in mind, this is quite a deep theorem, but having in mind this fact, we can identify the dual of lip 0 with the second dual of free Banach space, and now it's quite clear using this Rebiger theorem that our space on the left side is not sequentially complete. It's not weakly sequentially complete, so our space, original space lip 0e, is not Grothendieck. So we have another situation showing that our work is out of business. So we have still negative results. Okay, so for free, I mean, this is quite simple corollary. So we know that this space over this space lip 0 over James space is not Grothendieck. Okay, so let's put together some results stating that our work is just to show that lip 0 over something, it is something, this is our M, is not Grothendieck. So for example, M is separable Banach space, which is not weakly sequentially complete. This we tasted already. M contains a bi-Lipschitz copy of the unit sphere. For example, M might be CK when K is infinite compact space. So M is a net in little c0 or L1. I'm going to repeat this definition. Or M is just CK or L1 space or lip 0M or FM. So we have concrete classes of Banach spaces, and still the answer is negative. Okay, so this is the definition. Probably the problem with this time, I'm going to maybe to skip it. The definition of a net. Okay, and now let's recall the following concept. A metric space absolute Lipschitz retract if for all metric spaces P and M, P is included N, every Lipschitz mapping from P to M admits a Lipschitz extension to the whole space. So, for example, doing some result for Lindenstrauss, these two Banach spaces, little c0 and ck when k is metric compact, are absolute Lipschitz retracts. This is well-known fact. Okay, so now another collection of some selected facts, also negative. If E is a separable Banach space, which is absolute Lipschitz retract and contains little c0, and the object M contains a bi-Lipschitz copy of unit sphere of our space E, then the space lip 0M is not Grothendieck because we can construct a continuous linear operator on L1. So, and corollary is just a simple application of the theorem when E is just little C0. So if M contains a bi-elliptic copy of the unit sphere, then again, lib 0M is not Grothendieck. Okay, so now some open problems. I mentioned already that we know almost nothing about positive results, but there is nice relationship between even finite dimensional spaces M, still unknown results, now answers. The first question is the following. Does there exist a Banach space E of dimension at least 2 such that this object, lib 0E, admits a no continuous linear surjection onto L1? This is unknown. I hope this is still unknown. So of course, we can add some extra sentence. Can such space still admit a continuous linear surjection onto little c0? So another problem, this is the main problem of my talk, is there an infinite dimensional Banach space for which the space lib 0 is Grothendieck space? This we don't know. So, of course, the answer, positive answer to the problem 11, I mean that one here, would provide a positive answer to the first question in problem 10. So, it's interesting. And the special questions like, is there a reflexive Banach space such that lib 0x is a Grothendieck space, seems to be still open. More interesting, probably, because it has strong influence to many other questions, is the space lib 0 L over L2 a Grothendieck space? Even this very concrete question seems to be unknown. The answer seems to be unknown. Lib 0 over R square is a Grothendieck. For R, the answer is clear, because this is simple L infinity over R. This is Grothendieck. Okay, so now if you look at this dual of this space is not Grothendieck, because doing some joint paper, Cud, Kalenda, Kaplitzky, this dual contains FRN complemented, and we know that FRN is never Grothendieck. So now we have two possible answers for this crucial situation, lib 0 over L2. So if the space is Grothendieck, then lib 0 over Rd, when D is natural number, would be Grothendieck. You remember that even for R square is not here. The answer is unknown. So if lib 0 L2 is not Grothendieck, and by the way, it's possible to get an example of separable infinite dimensional Banach space E for which lib 0 is Grothendieck, then what is interesting, this situation would answer in a negative a question posed by Candino to Doha, whether lib 0 L2 is complemented in lib 0 F for every separable infinite dimensional Banach space. So there are nice collection of questions which are together, working together, fit together, but the essential point probably is just to look at or to try to answer problems 13 and 14. Very concrete, very concrete. I don't know, maybe somebody knows something about these problems, but up to now, I need to tell that I don't know. I think my time is over.